Okay. Hello guys. So we are going to be discussing the solution for RMO P6. Okay, so the problem is that we have a polynomial with integer coefficients and we want to prove that, and we're given that if we look at this sequence, then it never becomes divisible by n. And we have to prove that there are two integers a and b with such that they're different mod n and they give the same value. So I hope you can see this like the same thing. Okay, so first what we'll do is, okay, this notation like p of 0 and writing p a lot of times is annoying. So first of all, let's just say p to the n of x is the polynomial, which is p of x applied n times. Okay, this is n times. So yeah, like p of 1 of x is equal to p of x itself, p of x, and so on. Okay. So the key lemma which we use is that if p is a polynomial with integer coefficients, then a minus b divides p of a minus p of b for all a and b integers. So you can think about this as just if you're going mod a minus b, then it sort of respects the a minus b condition because all the things which we do in polynomials, they are like they respect modular arithmetic. So if you want to prove this formally, you can just expand it out and p of x is a1 a n x to the n. There's different n a k x to the k. Just blah blah blah. And now if you subtract it, you'll get, so each of the coefficients will be something like ai a to the I minus ai b to the ai times a minus b. Okay, so this thing will hold, just the proof of this lemma. So in particular, what this means is that it makes sense to go mod n in the polynomial. So you can look at p as a function from z mod n z to itself. Okay. And what we need to prove is that there exists some integers a and b which are both in this range and they're different, but the values are the same mod n. So suppose not, then essentially what this means is that p is injective. And since it's from the same from this set to itself, it also means that p is a bijection. But we don't really need that. Okay, so in this case, we're claiming that, so there will be a term which is divisible by n. In fact, that term will be p of 0, p square of 0, and so on. It will be not after p to the n of 0. Okay, so here's the argument. What we do is that these are n. Okay, let's also add 0 to this because it's a starting sequence. It's sort of p to the 0 of 0. And these are n plus 1 terms. So by PHP, we can get that there exist two terms which are the same, mod n. And now if those are p to the I of 0 and p to the j of 0, then okay, consider the minimal such terms. So if you have p to the I of 0 and p to the j of 0, then these are congruent mod n. We know that. And note that here we got that P is a bijection. So if these things, if I and j are both greater than 0, then this is just like P of P to the I minus 1 of 0. And this is congruent to P of P to the j minus 1 of 0 mod n. So by injectivity, we would get a smaller triplet. So you can essentially like keep taking it down by factor, which in turn implies that P to the I minus 1 of 0 is congruent to P to the j minus 1 of 0 mod n. Right? This we get because of injectivity. I don't know why this. Okay. So you can keep taking it down. So eventually we will get that since I is not equal to j, we'll get that if one of them will hit 0. So if I is less than j, then we will get that P to the j minus I of 0 is congruent to P to the I minus I of 0, which is 0 itself. P to the 0 of 0, so 0 mod n, which is what we wanted. So we've got a term in the sequence which is divisible by n, and this violates the condition. So yes, we have a contradiction. So the key idea behind the solution is just to note that. So if it is a bijection, then you can just consider the whole thing on z mod n z, go mod n on everything, and then it becomes a bijection. So you get a lot of nice things. Okay, hope it makes sense.